Hello everyone, my name is Wangjun Lee and today I'll be introducing our group's work, the anodic aluminum oxide template fabricated localized surface plasmon resonance sensor for the plasmonic coupling effect study. Our goal is to utilize the AAO substrates to fabricate localized surface plasmon resonance sensors and apply them for biosensing purposes. Localized surface plasmon resonance, or LSPR, occurs frequently in the rough nanostructures, usually referring to the nanometal particles. The surface charge on the nanometal particles is disturbed by an external electromagnetic force, causing polarization of positive and negative charges to oscillate back and forth. This phenomenon is known as surface plasmon. Surface plasmons absorb light waves with the same oscillation frequency, as shown in this figure, and produce an absorption spectrum. The peak of this absorption spectrum undergoes a redshift phenomenon as the refractive index changes. Therefore, we can modify probes such as antibodies and antigens on nanometals and observe the amount of redshift of the peak to quantitatively measure the concentration of analytes. Here we define the sensitivity as the redshift over the refractive index change. To enhance sensitivity, we utilize surface plasmon coupling effect. So the surface plasmon coupling effect refers to the phenomenon that when two paired nanoparticles approach each other from a distance, the peak of the sensor spectrum keeps shifting towards the red end of the spectrum. The longer the wavelength of the sensor, the more sensitive it is to changes in refractive index. Therefore, our goal is to study the behavior of surface plasmon coupling and use it to improve the sensitivity of the sensor. Currently, this technology has achieved many accomplishments. We can use this method to fabricate metal discs with different thicknesses and particle sizes, as shown in the right figure. Even on a rough FTO substrate, metal nanoparticles can be successfully fabricated using AAO templates. Next, we made the AAO LSPR chip using the following process steps. The first step is to modify MPTMS on the glass surface. The purpose of MPTMS is to enhance gold-glass adhesion, since gold does not adhere to glass. The second and third step is to place the AAO templates on the glass and remove the PMMA protection layer on the template through acetone vapor. The fourth and fifth step is to deposit 10 nanometer thick gold onto the surface through e-gun evaporation. After the deposition, we lift off the AAO template, and the result is gold nanodiscs that sits on the glass surface. Figure B shows the AAO LSPR chip incorporated with a microfluidic channel, which we would later use in our biosensing experiment. Figure C shows the optical setup. So the setup includes a light source, a spectrometer, a motorized stage, and a Lab-Smith microfluidic controller. To effectively predict experimental trends, we use the finite different time domain method, or FDTD, for simulation, with a periodic boundary and nanometal disk array structures, as shown in the figure. In figure B and C, we can see polarized electric fields on the gold nanodiscs, which indicates LSPR. The right table shows the parameters we simulated. with two periods 125 nanometers and 100 nanometers, with 3 different diameters each. And now we can see the sensitivity corresponding to each diameter. The figures are the SEM results of various AAO templates. After considering the template uniformity and fabrication accessibility, the template with period equals 125 nanometers and diameter equals 80 nanometers was selected for further gold deposition and liftoff process. The right figure shows the SEM images of AAO LSPR chip gold nanodiscs. We can see that the mean distance is 123.8 nanometers and the mean diameter is 86.2 nanometers, which is comparable to our expected parameters. Let us look at the sensitivity analysis. Figure A to C shows the simulated and experimental results. While the experimental results exhibited a relatively broader profile than the theoretical one, we observed that the sensitivity of the two cases was comparable. Above results suggest that the AAO LSPR sensor can be effectively fabricated using the AAO template. In the robustness analysis, we injected PBS into our microfluidic channel and observe absorbance changes over time. If the absorbance gradually drops, it indicates that the gold nanodiscs are gradually being washed away. Figures A and B highlight the importance of MPTMS in achieving strong adhesion between gold and glass. Specifically, after flow injection, the substrate without MPTMS exhibited a decrease in absorbance. In contrast, the substrate with MPTMS showed almost no absorbance difference followed flow injection. We tested the biosensing capability of our chip using genomic DNA from Colletrichum gliosporitis, a pathogenic fungus causing significant crop losses in hot and humid regions of South and Southeast Asia. Infected host plants display rotting flowers, rotting fruits, and leaves. Figure A shows the schematic of probe modification and target sensing. Steps 1 to 3 involve the probe modification process, during which we immobilize our DNA probe onto the gold nanodiscs. Steps 4 to 6 involves target sensing, and after target sensing, we regenerate our chip using NaOH. In Figure C, the wavelength peak in real time consistently redshifted during the surface modification process. The presence of a large amount of probe on the chip after the third modification step suggests successful surface modification. Following the modification, we introduced 250 nanomolars of target DNA into the chip surface, and a redshift of 0.7 nanometers was observed, indicating successful target binding. And in Figure B, it shows that the endpoint measurement after each step of fluid injection. We can see that absorbance peak consistently redshifted after probe modification and target binding. After probe modification, we injected various concentrations of target DNA. Figure D shows that the real-time peak wavelength consistently redshifted as the concentration of target DNA increased. We measured 5 sensing points for each condition, and all of them displayed similar wavelength shifts. The resulting calibration curve is depicted by the red dots in Figure E. Furthermore, we demonstrated that our chip can preserve its sensing ability even after NaOH regeneration, as shown in the blue line and the blue triangle in Figure E. In conclusion, we propose a simple and reliable method for producing gold nanodiscs using AAO templates. The nanodisk array exhibited a sensitivity of 120 nanometers per RIU, with high robustness, making it suitable for biosensing applications. And finally, sensors was successfully used for real-time multi-point detection of fungus genomic DNA, with a linear range between 0.025 nanomolars and 12.5 nanomolars, demonstrating its effectiveness in biosensing applications. I wish to express my gratitude to all those who have contributed to the successful realization of this scientific presentation, including my professor Nianzhu Huang and two of my teammates, Jiajing Xie and Guanjing Ye. Thank you for listening.